Hello everyone, welcome to topic 9.8, cell potential and free energy. By the end of this, you should be able to explain whether an electrochemical cell is thermodynamically favored based on its standard cell potential and the constituent half reactions within the cell. We are going to now combine Gibbs free energy with cell potential that we discussed in 9.7. So, as we saw in 9.7, chemical reactions can be used to generate electrical energy. By comparing standard reduction potential values in volts for the half reactions, we can calculate the standard reduction potential for the cell overall. Reactions that result in a positive voltage represent reactions that are thermodynamically favorable. These are called galvanic or voltaic cells. Reactions that result in negative voltage are not thermodynamically favorable and are called electrolytic cells. Unfavorable reactions require the input of electrical energy in order to proceed. This typically comes from an external power source, such as a power supply or a battery. Batteries are shown in a circuit connecting it to the wires with the symbol shown here. So if you take physics, hey, that might come up and you actually might use it for real. To calculate the voltage for a cell, we need to look at a table of standard reduction potentials. You can find those that are linked here. They're also, I think, in the back of your textbook, and I should have printed one for you. The table of standard reduction potential lists reduction half reactions in order from the most likely to be reduced, typically at the top, to the reduction half reactions that are least likely to be reduced. These would be at the bottom. The substances that are least likely to be reduced are most likely to be oxidized. Each half reaction has a corresponding voltage, which can then be used to calculate the value for the cell. The cell potential is calculated by taking the sum of the voltage for the reduction reaction and the voltage for the oxidation reaction. Note that the voltage for the oxidation reaction also has the same magnitude for the reduction reaction for that substance. However, the sign is changed because you flip the reaction around, thus flipping the sign. Also, if you multiply one or more of the reactions in order to balance the electrons, the magnitude of the voltage doesn't change. That stays the same. So you only can flip the signs. Since the voltage can be used to predict thermodynamic favorability, it is proportional to Gibbs free energy. We can use the potential of the cell, or in voltage, to calculate Gibbs free energy through the formula delta G equals negative NFE. In this equation, N is the number of moles of electrons transferred. F is Faraday's constant, and it has a value. This is given on the equation sheet. Make sure you pay attention to the fact it is coulombs per mole of electrons. The constant comes from the charge on an electron multiplied by Avogadro's number. Then E is the voltage. We need to note that for units to cancel, that 1 volt is 1 joule per coulomb. So when you do this math, I substitute out the voltage. So when I write the number E, instead of writing V for the units, I will write joules per coulomb, so my units cancel. Also remember that Gibbs free energy is typically given in kilojoules, so you may have to convert it either before or after. Okay? So in the equation, we will use joules. However, it is either given to us or asked to be given in kilojoules. Okay. So here we go. Calculate the value for delta G for the reaction given. Okay, so we need to write our equation. So it wants delta G. So hey, cool, it's already solved, so we don't have to do a whole bunch of rearranging. We know, so there's my N. I'm going to plug in for N here. We know F because it is always 96,485 coulombs per mole of electrons. And it's not mole, I need a space there. Mole of electrons. And we also know the potential for the cell is 0.7 volts, but earlier we just mentioned we need to switch volts to joules per coulomb so that the coulombs end up canceling out. We do not know what our N is. charges, or the number of moles of electrons. This is going to be the amount of electrons that are transferred. Okay, so when we look at this, we want to pay attention to what the total charge is on both sides. So we see positive 3s on both sides. That tells me that silver gives up a total of 3 electrons to gold in order to make 3 silver ions. So that tells me that in this reaction, I have 3 moles of electrons transferred, or 3 electrons are transferred for every reaction. So I'm going to write 3 moles of electrons. So now I can check my units, and I see coulombs cancel and the moles of electrons cancel because per mole is a denominator. So now I can multiply all these numbers together, and I get negative 202,618.5 joules. Now that is a really big number. Remember, Gibbs free energy really likes to be reported in kilojoules. So I'm going to quickly convert that by dividing by 1,000, and I get negative 202.62. I don't know, like, technically it should be 200 with the sig fig here, but whatever. Kilojoules. Okay, we know it is thermodynamically favored. One, because the cell potential is positive, and the other now is that our delta G for the reaction Gibbs free energy is negative. And a negative Gibbs free energy is a thermodynamically favorable reaction. Okay, so now we are going to look at our redo. So given the following standard reduction potentials, I want you to pause the video and write the balanced overall thermodynamically favorable reaction that occurs. So please pause the video and complete that now. Okay, so you should have gotten this answer for A. H2S plus Cl2 yields S plus 2 H pluses plus 2 Cl minus. You get that because when you compare these two values before changing the sign, you see that this one is smaller than this one. So this one has to flip its sign. Okay? And so when we flip the sign, we're going to flip the reaction because it'll be the one that'll undergo the oxidation rather than the reduction, because this is best at reduction, so the other one is forced to be oxidized. Then we add the half reactions, and we can cancel the electrons without multiplying because we have the same amount, and we get this reaction. Now you're going to take the reduction potentials and calculate the value for E in volts. Please pause the video and do that now. So when we have these two, just like how we added the two half reactions, our oxidation and reduction half reactions, we can then add their half cell potential. And so you should get 1.24 volts for this. Now looking at the moles of electrons transferred, that is what we canceled out, the number of electrons canceled out, and that is here. So that is 2 moles of electrons transferred. And now we can use all of this information to calculate the delta G in kilojoules for this electrochemical cell. So please pause the video and do that now. Okay, substituting what we got for C in C for N, 2 moles of electrons, then Faraday's constant is never going to change. Finally, I can change the units to joules per coulomb and plug that in for my potential. I'm also throwing in my conversion factor to change joules to kilojoules. And so you should end up with negative 239 kilojoules for this reaction. So that is also thermodynamically favorable because delta G is negative. Okay, so it's thermodynamically favorable. Okay, using these examples, I want you to complete the you-dos, check your work, and thank you guys for tuning in.